Okay, hello, welcome. This is going to be a new playlist on my channel, kind of a short course in differential equations. I usually do some of this stuff towards the end of my multivariable calculus class, but maybe you're just tuning in to get a little bit more knowledge on differential equations or to supplement your learning in a differential equations class. All right, so I think, in this video, I'm not going to be showing you any brand new techniques to solve differential equations. I am assuming kind of like a, AP calculus level of familiarity with differential equations, that you've done separation of variables, you've looked at slope fields, and most importantly, you know how to anti-differentiate. Okay, I'm just going to kind of presume those things. I'll do a couple of separation of variables problems in this video just to kind of remind you what that looked like and show you about, a way that it can go differently from AP calculus. But, for the most part, I'm going to kind of just take those as something that you already know. All right, so first, I need to define an ordinary differential equation. I'm going to start at the very beginning. So, I think, where I'm assuming you're at is that you know that a differential equation is an equation that gives you a derivative, or an equation that relates to, in some way, a rate of change. But I'm going to say that an ordinary differential equation has the form where, what makes it ordinary is going to be the fact that its solution is a single variable function. Okay, that we're not given a partial derivative. Okay, that would be a partial differential equation. That is a thing that we probably will not study in this playlist, but is definitely a very interesting and rich field of study in mathematics, partial differential equations. An ordinary differential equation has the form where, say like the nth derivative of some function y is given. So it'll be like y's nth derivative is given in terms of maybe its independent variable y and other derivatives, other, kind of lower derivatives. So the nth derivative of y is given by some function of maybe t, and I'll come back to that. T being my independent variable, y being my dependent variable, y prime being the first derivative of y with respect to t, and all the way up until, maybe possibly including the n minus first derivative, right? And, definitely do want to point out that, all right, in AP Calculus and all the way back to, Algebra 1, we used to talk about y equals f of x, okay? In this class, the solution to my differential equation is generally going to be y equals y of t, okay? And I want t to be my independent variable. Oftentimes we're talking about, with differential equations, we're studying science, population dynamics, things that change with time. So very frequently in this class, our independent variable wants to be time. And so our solution to our differential equation is generally going to be some function y equals y of t. I just wanted to point that out before I get too far and start talking about y of t, and you're wondering where f of x is. Okay, so an ordinary differential equation is just where we're given the nth derivative in terms of lower order derivatives y and t. So for example, something like y double prime is equal to 3y. Okay, maybe y prime equals t plus 1 over 1 minus y. This is looking like something we could probably solve with separation of variables, right? Or maybe, in the worst case, y's fifth derivative equals, y triple prime minus y divided by t plus y's fourth derivative. That one, somehow I think there's not going to be a solution to that. Okay. And I think that, it's a good example of these are ordinary differential equations because their solution is y as a function of t. And if you think about it, if y was a function of more than just t, if it took in 2 or 3 variables, it wouldn't really make sense to say the second derivative of y or the derivative of y, right? We would need the partial derivative of y with respect to one of its independent variables. Okay, so those are ordinary differential equations. And then I need to also tell you about the order of a differential equation, because in AP Calculus, we only dealt with first order differential equations, right? We only had dy dx equals, I don't know, something sometimes involving x and y, but we were never given the second derivative. So the order of an ordinary differential equation is the highest derivative. So in this, here it's n. Okay. Is the highest derivative in the equation. Okay. What else do I want to be telling you about? All right. Oh, and then kind of like, what are we going to be doing here over the time we're spending in this class? We are going to be, of course, trying to find solutions to the differential equations, right? But kind of what you realize is that there are kind of bigger questions. That you look at a differential equation, is there going to be a solution at all? Okay, we'll be able to develop tools to determine that just by analyzing the form of the differential equation and kind of what it's telling us. We'll have a theorem that'll tell us if there is going to be a solution. How many solutions are there going to be? Well, I'm about to show you where there's going to be more solutions than you might expect to a given differential equation. We already know that, if you have f prime of x equals 2x, well, then you're going to have a whole family of solutions, right? Anything x squared plus any number is going to solve that differential equation. And so, how many solutions are there? Even through a given point, there sometimes can be more than one solution. And of course, the big question is, how are we going to find them? What are the techniques we're going to use? And we're going to expand our library beyond just separation of variables in this course. Okay. All right. One thing I do want to point out to you is, I guess I'll start with doing some separation of variables. I want to start with a pretty basic differential equation that's oftentimes just like the first one that people start with in AP Calculus. I kind of just mix it in there with the rest of them. It's like, occasionally the exponential growth will show up and you have to solve it with separation of variables. I figure that there's so many things that you have to memorize in Cal BC that it's really not worth it to have you memorize the solution to dy dx equals k times y. All right. So, but for a good example of separation of variables, this is going to be where y prime is equal to k times y. Okay, this is going to be exponential growth. Okay. So the growth rate is proportional to the population. Okay. What was I thinking here? Oh, I'm going to change this into dy dt. And then I'm going to go for separation of variables. I'm going to get everything with y over here. So y dy equals k dt, and move everything with t over here. Okay, k doesn't really have to do with t. K is some real number, but I might as well just throw it over there. Okay, and I'm going to bring this back up here, and I'm going to take the antiderivative of both sides, because if two things are equal, then their antiderivatives will be equal as well. So antiderivative of y dy is going to be the antiderivative of k dt. All right, antiderivative of y dy, you know what that is. That's 1/2 y squared. What have I done? Oh, no. Horrible algebra error, but not worth re-recording the video, right? This is, how am I going to get exponential growth 5 1/2 y squared? That doesn't make sense. Okay, so antiderivative for 1 over y is log absolute value y equaling k times t plus c. Right, and then I'm going to get rid of the log by taking e to both sides power, and so I'll have absolute value y is equal to e to the kt plus c, which I can say that is e to the kt times e to the c. E to the c is just going to be some other constant, and that'll be c e to the kt. And then we know that if, say the absolute value of a is equal to 10, then a is going to either be 10 or negative 10. So I can say that y is going to either be c e to the kt or negative c e to the kt. And this is just the general solution, right? If I'm not given an initial condition, if I'm not given a point that this curve y of t passes through, this is as far as I can go. I can get up to a family of functions. And we know that for a given k, that's going to give us, say k is positive, it's going to give us exponential growth. And we would need an initial condition to find out the value of c, right? K is something that we already know. It's a fixed constant from the statement of the question. Okay, but if you see y prime is proportional to y, you know that, up to some initial condition, it's going to be c e to the k t. All right. Or this is like, I don't know, in your pre-cal class, you talked about per p e to the rt, it's the same exact thing. You just didn't look at it through the lens of solving a differential equation. Okay, so we did a little bit of separation of variables. I nearly bungled it, but we can move on. And, I may come back and record a different video on, some stuff that we can do with slope fields, because it is, it's pretty important to what we do here in differential equations. It's going to be the way that we graph a differential equation. I'm kind of limited here with the technology I have I can't draw you a really nice slope field. I can't start with a slope field and then draw on it. But maybe I'll go and I will, secure some technology and just record a video on slope fields. What else was I wanting to do? Oh, no, I am going to do some more separation of variables, but I want to show you something that can happen here. I'm going to just talk to you about a differential equation, and then I'm going to give you the solution, but I'm also going to show you that there are things that are going to happen here that we may not have considered last year. So the differential equation I'm interested in talking to you about is going to be, something like y double prime plus y prime minus 2y equals 0. Write that down. Y double prime plus y prime minus 2y. Equals 0. I'm going to ask you to consider, let's see, y1 equals c1 e to the t. Okay, I'm going to tell you this is a solution to the differential equation. Okay. We can verify that by taking the derivatives of y1. Okay, so y1 prime is going to be equal to, well, c1 is a constant, e to the t is its own derivative, so it's just going to be c1 e to the t. And y1 double prime, it's going to be the same thing. You take the derivative of e to the t and it's e to the t. So I'm going to have c1 e to the t again. And as for my differential equation here, I've got y double prime, c1 e to the t, plus y prime, c1 e to the t, minus 2 y's, well, y is c1 e to the t. What does that equal? I've got 2 of these minus 2 of them, that's going to be 0. Okay, so that fits the differential equation, means this is a solution. Okay. Then I also want to show you y equals c e to the negative 2t. So y2 is c2 e to the negative 2t. Hold on, just making sure that's right. Yeah. All right, I'm going to start by taking the derivatives just to kind of convince you. y2 prime is going to be, it's going to be c2 e to the negative 2t, but multiplied by negative 2 for the chain rule. So negative 2c2 e to the negative 2t. And y2 double prime is going to be, well, I'll multiply by negative 2 again, and that'll be positive 4. Wait, there's a c in there. 4c2 e to the negative 2t. And if we go and check what's going on here, y double prime is 4 of these. 4c2 e to the negative 2t plus y prime is minus 2 minus 2y, so that's minus 2 times c2 e to the negative 2t. Now look, I've got 4 of them, I lose 2 of them, I lose 2 more of them, I have none left. That is equal to 0, okay? And I'm happy, right, because I've satisfied that. Now these are each solutions in their own right. But if you think about it, if you added them together, their second derivative would be the sum of their second derivatives. Their derivative, the derivative of the sum, would be the sum of the derivatives. And the sum of their functions would be the function of their sum. I guess kind of sounded weird, but and as a result, I'm going to kind of claim that the, hold on, lost a piece of chalk. Just grab that one. I'm going to claim that the function y of t equals c1 e to the t plus c2 e to the negative 2t is a solution to this differential equation, right? Because if I just take the derivative of this, the derivatives of this part, run it through, I'm going to get 0. Same thing over there, and it's going to mutually satisfy it. And since we've got these two different parts and we added them together, I'm telling you there aren't any other parts. This is what we would call our general solution. And you can see, well, I'm going to need a couple of pieces of data to get C1 and C2. We're going to need 2 initial conditions. And, you know, part of the reason for that is that we've got a second order differential equation right there. And you remember, there were actually, I may have lied earlier when I said that in AP Calculus we only dealt with differential equations that were first order, because occasionally it was like, hey, acceleration is equal to this, find me the position function. That's going to be a second order differential equation, right? Because the acceleration is the second derivative of position. And maybe we even, like, you know, if f double prime is this, which could be f. But what we needed was we needed 2 initial conditions. We needed maybe a value of f prime and a value of f, or maybe 2 values of f. And so I just wanted to show you that this can happen, right? That there can be more solutions than just one, and they can, you know, maybe look a little different. Okay, maybe you could see how I came up with c1 e to the t and c2 e to the negative 2t. And if you can, then good for you. But we're going to come back on this type of differential equation, you know, later in this playlist. Okay. So, okay, I've got all of this. I've talked about all these things. And so now I just want to do a couple more separation of variables examples. I'm really not sure, you know, what I am and am not going to record for this playlist at this particular juncture. I'm just, you know, just starting out. And I'm kind of just going to go with, you know, whatever this year's class needs. But I may come back and record a separate video on separation of variables and, you know, the symbolic manipulation versus what we're actually doing here. But I may also just leave that to you know, the next instructor you have in differential equations. I might just focus this playlist solely on the solving and less on the kind of the analysis behind the scenes. So, but you know, before I end this video, I do want to do a couple of separation of variables problems and remind you of something you already know. So separation of variables is going to be where we're going to need it to be expressed as y prime is equal to f of y times g of t, in some sense. Like some function of y multiplied by some function of t. Or it better be able to be expressed like that, right? You know, last year we had to occasionally factor to make it separable. But we need to be able to write it as a product of just stuff with y's and just stuff with t's. And then, that's kind of maybe what I'll just leave that attached So, you know, a couple of examples of things that we could use separation of variables to solve would be, let's see, let's say y prime is equal to y over 1 plus t squared with y of, oh, that's going to be troublesome. How about pi over 4? I'm pretty sure that's what I want the independent variable to be. Y of pi over 4 is going to be, how about 2? I think that'll be good. All right, and then I'll do another one, dy dt equals t times y over 1 plus y squared. And these both fit that mold, right? In this case, the f of y is just the y that's in the numerator, and the g of t is the 1 over 1 plus t squared. Okay, so if we're going to try to solve these, well, I'm going to try to get everything with y over to the side. I'm not going to make that same algebra error again. 1 over y dy is going to be 1 over 1 plus t squared dt. And I can take the antiderivative of both of these things. That's log absolute value y. Antiderivative of 1 over 1 plus t squared with respect to t, that's inverse tangent, that's arctangent of t. And I'll have a plus c. As I'm getting rid of this, I'm going to end up with y equals plus or minus c e to the arctangent of t. Let's think about that for a second. And then I'm going to try to find my initial condition, or try to find my c using my initial condition. So when t is pi over 4, y is equal to 2. So 2 is equal to, this is a positive number, so I'll just say positive c e to the arctangent of pi over 4. Oh, that was not very smart, right? I thought I wanted it to be arctangent of pi over 4 so I could get 1. So c times e to the 1. That's going to be kind of annoying. But that just means that c is 2 over e, and that's fine. And y equals positive 2 over e times e to the arctangent of t. Okay, and that's a particular solution that came with an initial condition. All right, then over here, I'm going to, that one was pretty straightforward, just, you know, provided that you remember that the antiderivative of 1 over 1 plus t squared with respect to t is arctangent of t. But over here, this one's going to be a little different from the ones that we solved in AP Calculus, and I'll have a little more commentary on them as well. Let's see, what was I going to do? Oh, I'm going to get everything with y over there and hold everything with t on the right side. So when I multiply both sides by 1 plus y squared, I'll have that. I'm going to divide both sides by y. I'm going to have a dy, and that will be equal to t dt. I realized I was probably blocking by standing over there. That's equal to t dt. Which means that, okay, I can actually do this division, right? 1 over y plus y squared over y is going to be 1 over y plus y. So the antiderivative of 1 over y plus y dy is equal to the antiderivative of t dt. All right, and that's going to be log absolute value y plus 1/2 y squared equals 1/2 t squared plus c. Now, the thing is that in AP Calculus, the instructions were always like, find the particular solution y equals, in this case, f of t. The particular solution to the differential equation that passes through whatever. Well, that's not going to be possible. Even if I gave you an initial condition, like, I don't know, y of 0 equals 1. I think we could pretty easily figure out what the plus c would be there. But we're not going to be able to find y as a function of t because of this log and the squared. Algebraically, there's just no hope for us. Okay, so sometimes we have to be willing to settle with an implicit solution, right? An implicit equation that gives us a curve. But I also need to point out to you that there is another solution to this. And, maybe if I just pointed out to you that there is another solution, you could think of it. It's kind of a trivial solution. But y equals 0 does also solves this differential equation. It's like, what about that? If y is equal to 0, then dy dt is equal to 0. Equals t times y, which is t times 0 divided by 1 plus y squared, which is not 0. dy dt is equal to 0 for all t and y, right? But you can also say that if y is 0, y prime is equal to 0. So this fits the differential equation in a very boring way. And what I would do if you were sitting here in my class is I would kind of like shift your attention over to the screen and show you a Desmos thing. But this is something you can do yourself. I would go in and I would throw this equation into Desmos. Now, I'm not the biggest proponent of Desmos of all time, right? If you're in my class, you know that. It's good, it's a good tool, but it's not like something I'm gonna live and die by in my mathematics education, right? I prefer to stick to things that I can show you with basically zero technology. If you're gonna type this into Desmos, you do need to type this in log absolute value y like that, because it doesn't recognize that thing that's above the enter key on your keyboard. Doesn't recognize that as an absolute value. You need to use the ABS. Okay, so and then plus 1/2 y squared equals 1/2 t squared plus c. But what's really nice is you type that in and it's like, hey, would you like me to add a slider for c? And you should say, yes, I do want you to add a slider for c. And then if you go and you actually I feel like you can click on the slider or something and you can increase the range of c. I would recommend you kind of zoom in on the curve or on the picture, and then let c get pretty negative. Let it go to I think it goes negative 10 to 10. Let it go like maybe negative 100 to 100. And then you can make the jump a little bigger. And then slide that slider all the way for you, I guess it would be this way. Slide it all the way back to as far negative as you can make it. And you can see that solution y equals 0 is kind of the limiting case here as c goes towards negative infinity. And we'll have more to say about these other solutions and all sorts of stuff about differential equations in the later videos in this playlist. I just wanted to kind of give you a little appetizer of what we're going to be dealing with. So we're going to start with our separation of variables, but then we're going to add some good new techniques that should give you an advantage if you have to take this class at the next school. All right, so thanks for watching, and if you made it this far, I'm going to just go ahead and ask you to consider subscribing to the channel and maybe giving this video a like. Thank you.